Well, hello there. This video is all about implicit relationships and the derivatives that we can find from what we might call implicit functions. All right. If you've done the lab, you know that they're really not always functions when we deal with implicit functions, but we can still find their derivatives and we can still find slopes and tangent lines to these graphs. So just a quick little overview of what we're going to do. We got 6 examples to lead us through how to figure out the derivatives of implicit functions. A quick little introduction. An implicit function, in quotes, is one that has not been solved in terms of one variable alone, but an explicit function has. So, for example, y equals x squared plus 4 is an explicit function. Right? We've actually solved for y in this case. But x times y plus x squared times sine of y equals 4y squared is an implicit function, and this graph is right over here. So finding the derivative of an implicit function is just really an extension of us doing the chain rule. So the idea is that we want to find dy dx. All right, that's the ultimate goal, the derivative with respect to x. And if we can do that, we can reach our goal here. So, for example, find dy dx if y squared is equal to x. So as we're going through this, we want to take the derivative with respect to x of both sides. So we're going to take the derivative of y squared with respect to x and the derivative of x with respect to x. Well, the first side's easy. How much does x change as x changes? Well, it's a 1-to-1 ratio. They change at the same rate, right? So we get a 1 on the right side of the equation here. On the left side of the equation, though, we need to understand that y is some sort of a function of x. All right, we haven't solved for what it is. We don't know what it is, but we do know that there's some sort of an inside function, and we'll see that a little more clearly when I do the next part of this. But for now, just know that I'm going to take the derivative of a y squared with respect to x, and I get a 2y. But I also get a dy dx. Because of the chain rule, there's some sort of an inside function of y with respect to x. And our last step will be that we solve for dy dx. So if I divide both sides by 2y, I get my answer there. So why is this happening? Well, if y is a function of x, one way that we can rewrite this is off to the right here, and that's the y is equal to f of x. And we can rewrite this whole statement on the left as the derivative with respect to x of f of x squared equals derivative of x with respect to x. The right side is still equal to 1, but now it's a little easier to see why we've got the chain rule. If y is a function of x, this derivative is just 2 times f of x times f prime of x. That's the derivative of the inside function here by the chain rule. All right, so then if we were to solve for f prime of x, we get 1 over 2 f of x. Now, we don't like to write y, or excuse me, we don't have to have all this f of x here. So what we do is we write this dy dx notation instead of f prime. And we will leave our answer in terms of y. So y replaces f of x here. The dy dx notation will just open some more doors in the future for us. All right, so example 2, show that if x squared plus 2y is equal to x cubed plus 3y cubed, dy dx is equal to negative x times 3x minus 2 divided by 9y squared minus 2. So it looks complicated, but you just need to take it step by step, look at each piece, and take the derivative with respect to x. Anytime you see a y or something that's not x, you need to have a dy dx or a df dx or whatever the variable is, dz dx, right? If it's not x, you need to have an extra dy dx or something similar based on the chain rule, right? So if we take the derivative of the left side, we get 2x times 2 dy dx. That's the derivative of 2y with respect to x. On the right side, we get 3x squared plus 9y squared, that's the derivative of the 3y cubed part, times dy dx. That's the chain rule. So you got to respect the x, all right? In this case, anything with a y is going to have a dy dx with it if we're taking the derivative with respect to x. Once we've got that, then it's just a bunch of algebra. We're going to isolate dy dx. So in this case, I subtracted dy dx, 2 dy dx over to the right side, and subtracted 3x squared, and that moved to the left side. So now we got 2x minus 3x squared equals 9y squared times dy dx minus 2 dy dx. And now I'm going to try to get this to look like the form that I have here. If I factor out a negative x, you'll see that I end up with a negative 2, excuse me, and a negative 3, a positive 3x. So we have a negative x times a 3x minus 2 if I factor out a negative x. The reason why I do that is I wanted to get it to look like this numerator right here. When I solve for dy dx, I can divide by 9y squared minus 2 on both sides, and I get the answer that they gave me. All right, example 3, find dy dx if x times y is equal to 8. So notice I said x times y. Product rule, quotient rule, they can all still apply to this situation. So if we take a look at this, if I were to do the product rule, right, I list x times y, have my little x like with the other product rule problems. Derivative of x with respect to x is 1. Derivative of y with respect to x is called dy dx. Then I cross them together and I get the derivative of x times y is x dy dx plus y. This will be a useful thing for you to know. We're going to see this in a lot of different problems down the road. So this is a helpful derivative to have. So putting it all together, derivative of the left side is x dy dx plus y. Derivative of 8 is 0. If I subtract y from both sides and then divide by x, I end up with dy dx equals negative y over x. All right, consider x squared minus xy plus y squared is equal to 7. The graph of this rotated ellipse is right over here. As you can see, we can find tangent lines to this graph. We can find slopes of the function. It's just not a function in the normal sense that we know it. So first step, we want to kind of get an idea of how to find a point on this curve. So for example, they tell us that we want to show that negative 1 comma 2, which is right over here, is a point on the curve. Well, if we plug in x equals negative 1 and y equals 2, we should get a true statement when we plug this in. In other words, the left side of this should equal to 7. So when I plug in for x and for y, I get negative 1 squared minus negative 1 times 2 plus 2 squared simplifies to 7, which is correct. So this is a point on the curve because we showed that we got a true statement when we plug in x and y. Now find dy dx. In this case, the derivative of x squared with respect to x is 2x. We already learned that the derivative of x times y is x dy dx plus y. That was the previous slide. And I'm going to make sure I'm subtracting the whole piece of that. Plus the derivative of y squared with respect to x is 2y dy dx. Derivative of 7 is 0. So then I distribute my negative. I get 2x minus x dy dx minus y plus 2y dy dx equals 0. I want to isolate all of my dy dx terms. So what I did here was I added y to both sides and subtracted 2x. And I end up with a negative x dy dx plus 2y dy dx equals y minus 2x. All right, and then I can factor out a dy dx so that I can go through and solve for it. All right, and then when I divide by 2y minus x, the factored part of this, I get dy dx equals y minus 2x over 2y minus x. Lastly, let's see if we can find the slope of the curve at that point, negative 1 comma 2. It looks like it's a positive slope here. Let's see if that bears out here. So as always, in order to find the derivative, I know it's already in terms of x and y, so I plug in x equals negative 1 and y equals 2. You can see that I did that right here. And this simplifies to 4/5 as the slope of this tangent line. All right, show that if x to the 2/3 plus y to the 2/3 is equal to 4, dy dx is equal to negative y to the 1/3 over x to the 1/3. Let's take it step by step. We want the derivative with respect to x. If x is already there, we're already respecting it. So the derivative of x to the 2/3 is 2/3 x to the negative 1/3. Derivative of y to the 2/3 with respect to x has to have that extra dy dx because we need to respect the x. There's a y here, not an x. Y is some sort of a function of x. So for the second part, we get 2/3 y to the negative 1/3 times dy dx. Derivative of 4 is 0. Then we want to isolate the dy dx. So I subtracted 2/3 times x to the negative 1/3 on both sides. And then I want to solve for dy dx. So I get, since there's a 2/3 in both of these portions right here, I get negative x to the negative 1/3 over y to the negative 1/3. And of course, negative exponents can be flipped into the other side here. So we end up with negative y to the 1/3 over x to the 1/3. Okay, last example here. Suppose x squared plus y squared is equal to 25. This is a circle with a radius of 5. Find the second derivative and evaluate it at the point 3, 4. So to find a second derivative, we need to have the first derivative. So we find dy dx. Derivative of x squared with respect to x is 2x. Derivative of y squared with respect to x is 2y dy dx. And derivative of 25 is 0. When I solve for dy dx, I get dy dx equals negative x over y. Now, in order to find the second derivative, I can use the quotient rule. All right, so I've got negative x over y. So we say low, which is y, times d high, which is negative 1, minus high, which is negative x, times d low, which is dy dx, derivative of y with respect to x. We're still respecting x here, right? We can see that in our denominator. And all this is over y squared. Now we know what dy dx is. We can just plug in negative x over y for dy dx, and we got our formula in terms of x and y. If we want the second derivative at 3 comma 4, we plug in 3 for x and 4 for y. And in this case, we plug in negative 4 plus 3 times negative 3/4 all over 16. This simplifies to negative 25 over 64. So in summary, implicit differentiation is just an extension of the chain rule. You got to give the respect to x. If you don't have an x, you need a dy dx or a dl dx or dz dx or df dx, whatever the other dependent variable is. You still got to respect that independent variable. All the other ideas of differentiation, the product rule, the chain rule, all apply here. We'll see plenty of examples of that going forward. And then, of course, we can also find tangent lines and second derivatives. Thanks for watching. We'll see you on the next video.